Hello students. So yesterday we had seen how to construct a linear programming problem from a given real life situation. So today we will discuss a few more problems so that you can get yourself acquainted with the process of formulating this linear programming problem. So I have taken one question, as you can see. The question reads as follows. A home decorator manufactures two types of lamps, A and B. Okay, and both lamps go through two technicians. First a cutter and second a finisher. Okay, so two types of products are produced, or two types of lamps A and B are produced, and during the manufacturing process there are two stages. First is a cutting stage and the second is a finishing stage. Okay, so both the lamps have to go through two technicians, so there are different technicians for this cutting and for finishing. Okay, so some more information is given. Lamp A requires 2 hours of cutter's time and 1 hour of finisher's time. Okay, and lamp B requires 1 hour of cutter's time and 2 hours of finisher's time. Okay, so that means each lamp A, each product of lamp A, or each unit of lamp A requires this many hours. Okay, similarly each unit of lamp B requires these many hours. Now the cutter and finisher, they are also workers of the company or home decorator, so they are available for a certain period of time. Okay, not more than that. So the cutter has 106 hours and the finisher has 76 hours of time available each month. Okay, so every month they have, the cutter has 106 hours of work time. Okay, so the cutter does not work more than 106 hours and the finisher does not work more than 76 hours. Okay, each month. And profit on lamp of type A is rupees 6 and on the lamp of type B is rupees 11. So formulate this problem as an LPP so as to maximize the profit earned in 1 month. Okay, so this is basically our question. So how will we solve it? So we need to find out how many, or we need to formulate this problem so as to maximize the profit. Okay, so profit earned per month. Okay, so let us take x number of, let x number of A lamps, okay, A lamps be produced per month. Okay, per month, and let y number of B lamps, okay, be produced per month, right? So what are the constraints that are available? So first of all, let us write what is the profit. Okay, so the profit function is given by z equal to, so profit on type A lamp is 6 rupees, so it's 6x, plus profit on type B lamp is 11 rupees, so it's 6x plus 11y. So the profit function is this. So immediately we can understand that since it's a profit function, we need to maximize it, so it's a maximization LPP. Okay, so our objective function here will be maximize z equal to 6x plus 11y. Okay, next we need to look for some that is restrictions. So here we have this restriction: lamp A requires 2 hours of cutter's time and 1 hour of finisher's time, and lamp B requires 1 hours of cutter time. Okay, so if we manufacture x units of lamp A, then how much or how many hours of cutter's time is required? we require exactly twice x hours, right? And for y units of lamp B, we requires y hours of cutter times. Okay, so total how many hours of cutter's time is required? It's twice x plus y. Okay, right? So total cutter's time required is equal to what? Twice x, because each lamp A requires 2 hours of cutter's time and each lamp B requires 1 hour of cutter's time. So total cutter's time required is twice x plus y. Okay, and by question the cutter is available only for how many hours? It's given in the question. The cutter has 106 hours. Okay, so by question the total cutting time, that is twice x plus y, this cannot be more than 106. Okay, so by question twice x plus y is less than or equal to 106. Okay, similarly total finisher's time required is how many hours of finisher's time is required? Lamp A requires 1 hour of finisher's time and 2 hours of lamp B requires 2 hours of finisher time. So it's just the opposite. So it's x plus twice y. And again by question the finisher is available only for 76 hours. So x plus twice y has to be less than or equal to 76. Okay, hence the given problem as an LPP linear programming problem is, okay, so how do we write it? We write it this way: maximize z equal to 6x plus 11y subject to the constraints twice x plus y, this is less than or equal to 106, then x plus twice y, this is less than or equal to 76, and x comma y greater than or equal to 0. Okay, so the last constraint is the non-negativity constraint and it should be always placed. Okay, so I hope this is clear. Right, let us read the question again. A home decorator manufactures two types of lamps, A and B. Okay, so both lamps go through two technicians, first a cutter and a second a finisher. So lamp A requires 2 hours of cutter's time and 1 hour of finisher's time. Lamp B requires 1 hour of cutter's time and 2 hours of finisher's time. So the cutter has 106 hours and the finisher has 76 hours of time available each month. And profit on one lamp of type A is 6 and on one lamp of type B is 11. Okay, so the profit function here we have got, it's 6x plus 11y. What is x? X is the number of A lamps that is produced per month and y is the number of B lamps that is produced per month. Okay, and then we have formulated these constraints. The total cutter's time required is twice x plus y and the total finisher's time is required is x plus twice y. So by question x plus twice x plus y is less than or equal to 106 and x plus twice y will be less than or equal to 76. Okay, so the given problem can be formulated as this LPP: maximize z equal to 6x plus 11y subject to the constraints twice x plus y equal to less than or equal to 106, x plus twice y less than or equal to 76, and x and y are both non-negative. Okay, so this is the solution of the problem, not the solution actually, mathematical formulation of the problem. So if in your exam if you are asked formulate the problem mathematically, then this much is sufficient. Okay, and if you are asked to solve, then we have to do something else, which we will be doing in the next classes. Okay, so let us see another problem of this type. So a firm manufactures two types of products, A and B, and sells them at a profit of ₹2 on type A and ₹3 on type B. Okay, and each product is processed in two machines, M1 and M2. Okay, so each product is processed in two different machines, M1 and M2, and type A requires 1 minute of processing on M1 and 2 minutes on M2. Type B requires 1 minute of processing on M1 and 1 minute on M2. Okay, and the machine M1 is available for not more than 6 hours. M2 is available not more than for 10 hours during any working day. So formulate the problem as an LPP so as to calculate how many products of each type should be produced per day to maximize profit. Okay, so actually this part, and then if this is the question, then we need to solve the problem. Okay, so I had taken the problem directly from the question paper or book. So that way, so as of now we are just doing the formulation part. We are not finding out exactly how many products of each type should be produced per day, okay, to maximize profit. So this problem is very similar to this earlier problem, as you can see. So here in the earlier problem, each product passes through two stages, that is cutter and finisher. Here each product passes through two different machines. Okay, so it's almost a similar type of problem. So immediately you can do it. So let X units of A be produced. So produced per day or per week, that you have to see from the question. Okay, any working day, so per day, so let us keep it as day. Let X units of A be produced per day. Okay, and let Y units of B be produced per day. Okay, so by question, A requires 1 minute of processing on M1 and 2 minutes on M2. So total processing time on M1 is what? Total processing time on M1 is equal to what? So A requires 1 minute of processing on M1 and B requires 1 minute of processing on M1. Okay, so total processing time on M1 is exactly X plus Y. Okay, because each requires only 1 minute of processing. Next, total processing time on M2 is what? The lamp A requires 2 minutes of processing on M2 and lamp B requires the product B requires only 1 minute of processing time in M2. So remember, these are in minutes. Okay, so you have to take care of the units also. These are in minutes, right? But by question, the machine M1 is available for how many minutes? X plus Y. This is less than or equal to, you can see the machine M1 is available for not more than 6 hours. So that is given in terms of hours, but our this time is here is in minutes. So we have to convert this to the same units. So not more than how many hours? 6 hours. Yeah. So 6 hours means actually 6 into 60, that is 360 minutes. Okay. So this has to be X plus Y less than or equal to 360 and twice X plus Y, this is less than or equal to, so the other one is available for 10 hours. So 10 hours means actually 600 minutes. So twice X plus Y is less than or equal to 600. Okay, and what is the profit? Z equal to the profit earned is 2 rupees on A and 3 rupees on B. So the profit Z is twice x plus 3y. Okay, so this is the profit function, right? So how will you formulate it mathematically? So mathematically the given problem is maximize z equal to twice x plus 3y subject to the constraints or restrictions x plus y is less than or equal to 360 and twice x plus y, this is less than or equal to 600 and x comma y greater than or equal to 0. Okay, so these are the this is the mathematical formulation of the given LPP. Okay, so I hope it's clear. Okay, so similarly you have another problem. Let us have a look at this problem also. So two grades of paper X and Y are produced on a machine. So because of raw materials restrictions, not more than 400 tons of grade X and 300 tons of grade Y can be produced in a week. Okay, and there are 160 production hours in a week. It requires 0.2 hours and 0.4 hours to produce 1 ton of the products X and Y respectively, okay, with corresponding profits 20 and 50 per ton. So formulate the problem as an LPP so as to maximize profit. Okay, so there are two types of product, capital X and capital Y. Okay, so let us suppose that small x units of capital X is produced, right? Produced in a week, okay, produced per week, let's say, right? And y, small y units of capital Y be produced per week. Okay, so because of raw material restriction, not more than 400 tons of grade X and 300 tons. So here the unit that we are taking is tons. Let X tons of capital X be produced, Y tons of capital Y be produced per week. Okay, so the restriction is not more than 400 tons of grade X can be produced. So what is this restriction? This means that X is less than or equal to 400, okay, and Y is less than or equal to 300. Okay, so these are the two constraints that we get readily. Next, then other constraints are there are 160 production hours in a week. Total production hours is 160. So for type X, each unit requires 0.2 hours. Okay, so the total production time is 0.2 times of X plus 0.4 times of Y. Okay, this many hours. So this is less than or equal to 160. Here everything is in hours. So 1 ton requires 0.2 hours of time, okay, or processing. So X tons will require 0.2 into X, right? 1 ton requires 0.4 hours of processing. So Y tons will require 0.4 into Y hours of processing. Okay, so this constraint is there, and the value of Z is 20X plus 50Y. Okay, so we have already got our LPP. Please try to do it yourself. I am just providing the hint. Okay, so how will I write it? We write it this way: let X tons of capital X and Y tons of capital Y be produced per week. Okay, week. So profit is Z equal to 20X plus 50Y. Okay. and by question we have x is always less than or equal to 400, right? X is less than or equal to 400 and y is less than or equal to 300. Okay, so these are already there. And total production hours required is actually 0.2 times of x plus 0.4 times of y, and so by question 0.2 times of x plus 0.4 times of y, this has to be less than or equal to 160. Okay, so the problem as an LPP is, so how do I state this problem? You can state it this way: maximize z equal to 20x plus 50y subject to the constraints what are the constraints? X is less than or equal to 400, y is less than or equal to 300, and 0.2 times of x plus 0.4 times of y, this is less than or equal to 160, and x and y, they are greater than or equal to 0. So these are the this is the mathematical formulation of the given LPP. Okay, so in the next class I'll also take up two other problems which are called diet problems, so which requires the formulation of a diet plan. Okay, so how much food of different types you should intake in order to meet the daily vitamin mineral requirements. Okay, those type of problems are there. We will discuss that, and then we will move to graphical solution of LPP. Okay, so I request every one of you to please kindly prepare yourself for plotting graphs. Okay, how to plot graphs of this straight lines. Okay, how to plot graphs. Suppose I have the straight line y equal to x plus 2. Okay, so how will the graph of this straight line look like? Okay, so y equal to x actually represents this straight line which is having slope 45 degree, that is slope 1. Okay, and y equal to x plus 2 when it has y intercept 2, so y equal to x plus 2 is somewhat like this. Okay, so it will have the same slope as the y equal to x, and it will have y intercept 2. Okay, so the graph of y equal to x plus 2 is somewhere here, right? So these ideas will be required. If I have something like y equal to minus x plus 2, okay, so how do you plot this graph? Y equal to minus x plus 2, y equal to minus x, it represents straight line with slope minus 1, okay, and passing through the origin, right? So let me just rotate it a little bit. So somewhat like this, and then it passes through this and has y intercept 2. Okay, so it's something like this: y equal to minus x plus 2. Okay, so we need to understand this type of plots. Okay, how do I plot it? In particular, if I say a straight line of the type which is given in intercept form, that is say something like x by a plus y by b equal to 1. Okay, so how do I plot that straight line? Okay, so how to plot that? It's quite simple. So a is the x intercept and B is the y-intercept. So suppose the x-intercept is somewhere here and the y-intercept is somewhere here, there. Okay, so once you know the x-intercept and y-intercept, it's very easy to plot the graph. Okay, so suppose this length is suppose your A, it is the x-intercept, and this length is B, that is the y-intercept. So this is the graph of the straight line. Okay, so all these things will be required in the subsequent classes. So for today we have this much. We will meet tomorrow again. Thank you.